The University of North Carolina at Chapel Hill is developing a telepresence video wall for enabling informal conversations between remote coworkers. In this project, 2 video walls have been constructed at UNC. Each video wall consists of 4 large screen displays and a teleconference audio system. Eye contact is facilitated by switching between 2 sets of cameras as people approach the displays to speak with one another. The first set of panoramic cameras captures a wide-angle overview of the room. A second set of personal cameras are positioned in front of each display at eye level to help people make eye contact during conversations. Image segmentation is employed during this switching process to remove distracting duplicate image artifacts that occur when a person or object is seen by more than one camera. Microsoft Kinect depth sensing cameras are used to improve this image segmentation process and address 3 long-standing challenges in the areas of foreground-background segmentation, foreground-background alignment, and background image hole filling. The team is also exploring advanced offline image segmentation algorithms for improving image quality along edges. The team has implemented 2 depth-based image segmentation algorithms that take advantage of depth information for segmenting people and objects from the personal and panoramic cameras. In the past, the team relied on 2D background subtraction. Image segmentation required a static background, and moving people and objects in the background often led to distracting artifacts when misclassified background pixels appeared to be connected to people who were speaking in the foreground. The introduction of reliable depth information from depth-sensing cameras has since reduced this static background requirement. The first algorithm is used in the real-time video wall system and starts with reading depth map images from each Microsoft Kinect camera. Each depth map pixel is projected into 3D space to create a point cloud. The floor is removed using a clipping plane that is located just above the surface of the floor. 3D points below this clipping plane are removed, and the remaining 3D points are back projected onto each panoramic and personal camera image. Back projected 3D points on the panoramic image are used to eliminate people in the foreground. The same back projected 3D points on the personal camera image are used to retain only those people in the foreground. Here is a composite image result with the personal camera pixels in front of the remaining panoramic camera background pixels. The panoramic background ensures a consistent, comprehensive view of the distant room across the 4-panel display. At the same time, use of the personal camera pixels from the foreground person ensures good eye contact with nearby people during conversations. Next, we address the problem of transitioning between camera views. If a person is close to the display, we superimpose his or her personal camera image over the panoramic background to facilitate eye contact during conversations. Otherwise, we show his or her image in the panoramic camera view. This results in a problem. The location of the foreground person in the panoramic and personal camera images is not guaranteed to be exactly the same. For example, in the personal camera, the person might be in the middle of the image, and that same person in the panoramic camera may be off to one side. This offset can cause a distracting snapping transition. The team's solution to this problem is to place and size the user's image in the personal camera to match where they would be in the panoramic camera view. In addition, a 2-second 3D animation is added to ease the transition between the user's orientation in the 2 camera views. The team has observed that people appear to be moving or gliding when viewed from a stationary perspective. However, this effect is hardly noticed as people approach the display to speak with one another. The team's depth-based hole-filling algorithm responds to a problem that occurs when a person or object is removed from the panoramic background, but is not completely covered by superimposed foreground pixels that are segmented from the personal camera view. The resulting holes can be filled one of 2 ways. First, real-time 3D point cloud pixels can be displayed, and second, a static background image taken before users enter the room can be used to fill remaining pixels. The team is exploring advanced segmentation methods that incorporate color and depth information for making edges of the foreground user less noticeable during conversations. Erode and dilate operations are used to construct a trimap. The white layer is slightly smaller than the original mask and represents pixels that we are certain are in the foreground. The outline of the black layer is slightly larger than the original mask and represents pixels that we are certain belong to the background. The third layer represents pixels that may or may not contain an edge. The exact location of this edge is calculated by iteratively sampling nearby foreground and background pixels from the white and black trimap layers. The optimized color sampling for robust matting algorithm is applied to find an optimal solution. The resulting video wall enhancements have incorporated depth information to successfully account for multiple overlapping people, align foreground and background images across video wall panels to maintain a spatially consistent view of the room, and fill holes in the background by replacing pixels with real-time 3D depth and historical image information.